Yes. Okay, yeah. So I'll explain, piece by piece what this title means. But everything today is based off joint work with my advisor, Alan Fries. So yes. Okay. We're going to be talking about hash tables, which is an example of a data structure. And so I assume everybody, like, to some extent knows what data structures are. Probably you've taken a class that has like data structures in the title or something like that. But I'm still going to go through what a data structure is just as it relates to the talk, right? So a data structure, you want to store a whole bunch of objects, say n. N is going to be our number of objects throughout the talk. And you want certain properties when you're storing these objects. You don't want to use too much space, right? So each object, we assume they're all like the same size. They take up some amount of space. We don't want to use too much more than the minimal amount of space, which is n times the number of objects. We want to be able to add new objects. If you say, put this object into your data structure, we should be able to do that quickly. Similarly, we want to delete objects from your data structure. And it's important to answer a question. I give you some object and I say, is this in your data structure? You should be able to tell me yes, no, very quickly. So some examples of data structures that maybe perform more or less well on these criteria. A basic array. That doesn't do too well when you ask, hey, is this object in your array? You kind of have to look through the whole thing. That's annoying. So maybe you could try to sort it, but then it's like hard to insert stuff. So then we have linked lists, hash tables. Hash table, that's the one that this talk's going to be about. Binary search trees, all kinds of other ones. So we'll remember all our criteria. So I got a list of data structures from degocheatsheet.com that tells me the runtime of some of these operations on them. The one we're looking at is hash table. And it seems like hash table is like a pretty good data structure because it has constant time, search, insertion, and deletion. And in fact, it's like the only data structure that has those, or at least the only one that made it to this chart that has those. So that's what we really hope to have from hash tables, and we also want this space complexity to be good. Any questions? I don't know, probably not yet. Learn data structures? I mean, I guess I don't. I guess. Well, you'll see how like data structures relate to this talk, but I don't know too much about. Like, I really only know about like this specific type of data structure. So, So hash tables. So you have some hash function from your set of objects to your table slots. Now, what does this function look like? We want it to look as random as possible. Basically, we want to assign every object to a random slot at the table. But on the other hand, it has to be the exact opposite of random. It has to be completely deterministic, because like if somebody comes up to, if we put some object A in our table and then somebody comes up to us and says, is A in your table or not, we need to know where to look for it. So we need to have some deterministic function that looks kind of random. So like you want to somehow mix it around deterministically till it looks random. Okay, so my favorite example of a deterministic but random looking function is people's birthdays. So everybody has a birthday and it stays the same throughout your life. But it's kind of uniformly distributed throughout the year, mostly over the 366 days. Tomorrow is leap day, very exciting. But okay, maybe it's not quite as uniform over leap day, but like it's sort of uniform. So when you make your hash table, you make a slot for every day of the year. And then you put people in the hash table based off when their birthday is. So Theory Lunch organizer Noah Singer, his birthday is March 29th. So we put him in the March 29th slot in the table. Oh, I just do. I don't know. I know a lot of other people's birthdays. Here's a bunch of other like normal Theory Lunch attendees who I happen to know their birthdays in the table. So you store everyone in their position in the table of when their birthday is. And then it's very quick to insert new people. If somebody says, oh, I need to be in your table, you say, what's your birthday, right? And then you just put them there. And if somebody said, is so-and-so in your table? You say, I don't know, what's their birthday? And you look at that slot in the table to see if their birthday is there. And so it works really well. And like there's 366 spots. So of course we can't store more than 366 people. But like, probably if we have like 100 people in the room, I'm sure, like, no two of them will have the same birthday, right? I mean, we all know. I mean, that would be some sort of like paradox or something. If, okay. Some people have the same birthday, so that is a problem. That we might get two people who have the same birthday, and then we have to be able to deal with that. So that's what we call a collision in a hash table when the hash is the same. And so for theoretical analysis of collisions, and in fact throughout this talk, we assume the hash function is a uniformly random function, even though it's the complete opposite of that because it's deterministic, but it looks like a uniformly random function. And so then we can say, oh, what's the probability when I add the ith person that somebody else already had their birthday? It's I minus 1 over m, because that's how many slots are full. And so then the probability, so that's the probability that everyone gets their own slot. We do our classic like estimation of 1 minus x by e to the minus x, and then we get that's about the probability of a collision for n objects into m hash table slots. And so the threshold when a collision is like 50% likely to happen is about n squared. So to store n objects into a hash table with no collisions, our hash table has to be size n squared, which is just massive because n is like, a million or something. So it's like a million times the minimal size. So that's pretty terrible. So we succeeded on 3 of the conditions on insertion, deletion, and query, but our space was horrible. So if we want to do better on space, we need to find a way to deal with collisions, right? We can't just say, hope there's none, Okay, any questions so far? Okay, probably all of you have like learned about this stuff, I guess, right? Okay, anyway, so one way to solve collisions is linear probing. If you're inserting somebody, you say, what's your birthday? If nobody has that birthday, you just give it to them. If somebody else already has their birthday, you say, can you celebrate your birthday the next day instead? And they're like, oh, okay, sure, I can celebrate my birthday a day late. And then you put them into that slot. And so then querying, so this is linear probing, this method. And so querying, you say, what's your birthday? You look there. If they're there, you found them. If there's nobody there, they're not in there. But on the other hand, if somebody else is there, their birthday might have been kicked down the line. So you kind of have to like walk down the line until you find them. But then deletions are kind of complicated because we can't just delete somebody because then there's like an empty spot that'll tell us that will think we can't find somebody's birthday. So deletions are kind of hard in linear probing, but you can do them. There's tombstones and stuff. You can put markers in the deletions. Okay. Yeah, you can ask questions at any time if there's any questions about this, but I think so anyway, so one thing people talk about with linear probing is primary clustering, which is like almost what's happening down here, where just like by random chance, a lot of people have like very similar birthdays. And so then they kind of all like end up in a line of full birthday slots. And then when we insert a new person, they have to move like way down the line until we find an open birthday. So that's called primary clustering. And it's a problem. And it's just terrible, and we have to give up on linear probing altogether, and nobody can fix it, except this guy. This guy's William Kuzmal. He's going to become a CMU professor this fall. He's coming here, and he gave a theory lunch talk like a year ago about linear probing and something called graveyard hashing, which was his way of doing linear probing. And he says primary clustering actually isn't that bad. Depending on how you do deletions, it can make a big effect. So actually, linear probing is pretty good. It's so good that it's like kind of the main thing people do in practice. Linear probing hash tables are great. So like if you're in like a coding interview or something, and they're like, how should I store this data? Just tell them like, oh, use hash tables because it has like O of 1 stuff and use linear probing. Anyway, but that's not as interesting. So that's not what we're going to talk about this time. But we're going to learn the type of hashing we're going to do instead of linear probing. It does have some advantages over linear probing. So I'll explain the advantages of our hash method instead. Yeah, so back to the title slide. I've explained to you now what hashing is, and you can kind of figure out what O of 1 insertion is, but we don't know what random walk d-ary Cuckoo means yet. So I need to explain these words to you all. So the next word I'm going to explain is the word cuckoo. Okay, so cuckoo, it's a type of bird. It's called that because that's the sound it makes, like cuckoo, cuckoo. Okay, there's a picture of it up there. So that's a cuckoo baby bird with a a warbler behind it holding a dragonfly in its mouth. To explain what's going on there, we have a nature documentary about cuckoo birds to watch. Okay, I think that's enough nature documentary. But so what is the point? So the cuckoo bird comes to another bird's nest, and so the cuckoo chick gets laid in this nest, and then it hatches and it pushes out the other birds out of their nest, and the egg is like fall into the water. And so that's kind of what cuckoo hashing does. A new thing gets inserted and it kicks out the old thing. Except the only difference is the old thing doesn't just like die by falling into water. It's like I don't know, if you were like some kid and like ask your parents like, oh, what happened to the eggs that got pushed out of the nest? Your parents might say like, oh, they landed in another nest. And so that's what's going to happen in cuckoo hashing. So it'll be like the happy form of cuckoo birds, like cuckoo birds if everything worked well. So how does that work? So instead of one hash function, we have two hash functions. Say one is the person's birthday and one is the person's mother's birthday, which is probably uncorrelated to their own birthday. For instance, Noah's mother's birthday. Yeah, so the point is, so there's two hash functions, two possible slots you can insert it in. If either one of them is empty, you could just put it there. But if both of them are full, what do? You put it in one of those two slots, and the thing that was there, it also has two hash functions, right? So you just send it to its other hash function, right? Like say it was currently in its birthday spot, then you kick it out, and now it goes to its mother's birthday spot. And then if there's something there, it kicks them out, and keeps kicking out until eventually someone lands on an empty slot. And so there's kind of like a problem with this. So you might say, you know, is it even going to eventually land on an empty slot? It could just like cycle around and repeat forever, or like it might take a really long time to land on an empty slot. But hopefully, well, we'll see later. It turns out to work. But then once we have everyone assigned to either their birthday or their mother's birthday, then finding people is easy. You know, if we say, oh, is so-and-so in your table, you say, oh, what's your birthday? What's your mother's birthday? We only have two spots to check. It's not like linear probing where we might have to check through a whole lot of spots. They're always going to be in one of those two spots. So that's really nice. Deletion is also super easy. We can just find where they are and just remove them. I mean, we don't have to leave any tombstones or anything. So that's great. So deletion and search are both very easy. We're not totally sure about insertion yet, but definitely deletion and search are very easy. And so nobody could complain about how fast deletion and search are. Oh, except this guy couldn't complain because he said, okay, in linear probing, a lot of times if something's not in the table, you only need to check one thing. And you check that one thing and say, oh, it's not there, we're done. And so in cuckoo hashing, you always have to check two things. So that's a little slower, but that's only true, like in linear probing, that's only kind of true if your load factor is pretty small. Like if your load factor is like the percent full the table is, okay. So like if the table is not that full, that's true, but like once it gets pretty full, probably the first place you go to is going to be full. So anyway, so I'd say that's only true of low load factors, and we kind of want to be thinking about like pretty high factors anyway.
There might also be some locality.
Yeah. Oh, well, this is for, he's saying for negative queries, so we assume the query is like independent.
Yeah, but I'm saying if you do linear programming and then you have to probe.
Oh, yeah.
Probing like adjacent spots might be cheaper than probing to like unfolding.
Oh, I see, like in a computer. Yeah. Yeah, that could be true too. So that might be another reason you might like linear probing. But anyway, but I think this is better because cuckoo hashing, you know it's always going to be two. Like the worst case is still only two tests. And then he said d greater than or equal to 2. That's for d-ary Cuckoo hashing, which is what we're going to soon learn about. Okay, does the cuckoo hashing algorithm make sense? If it doesn't, you're definitely not going to understand what I say about the proof. So. Okay. Okay, cool. We'll go on. So cuckoo hashing was invented in 2001, so not even that long ago, really. And it has like over 1,000 citations. People use it in practice, like actually like in the real world, as well as in theory. It's good for both purposes. It has guaranteed fast query and deletion, as we were talking about. And here's the big like theorem that says cuckoo hashing works. Okay, if the hash table is less than 50% full, then with high probability, okay, so first off, we just need, in order for the insertion to even like terminate, we need there to be an assignment of objects to one of their two possible slots, such that each slot only gets used once. So we need a matching like that. So with high probability, there does exist a matching. And even more than that, the expected insertion time, like the number of times we have to kick out someone and like, you know, do this cuckooing process, is O of 1. So it doesn't, you know, it doesn't grow as the hash table grows. So cuckoo hashing works. Yay. On the other hand, if your hash table is more than 50% full, then probably there's not even an assignment of objects to slots. So, yeah.
So I have two questions about this result. So one, you say the expected time is O of 1. Can you also say some like with high probability it's O of 1 or log n or something? Or-
Yeah, I think the insertion bound, yeah, so there's some work on it. Yeah, so I think the insertion bounds are like exponential tail. So yeah, so like the probability of it taking longer than like s steps is like e to the minus s.
And my other question was, does this only actually rely on like some k-wise independence or something of the hash functions, or do you really?
So there's also results of that. So there is also results on, yeah, so it does only require some k-wise independence. There's a result of like Daniel Kane and someone else that says, oh, like something wise independence is all right.
Yeah.
For me, hash functions are totally independent. That's what I'm analyzing. Okay, but like, yes, there is lots of work on here's an actual family of hash function. It's good enough. That makes sense. Yeah.
So the with high probability statements presumably like smoothly transitions. It's not like a cutoff
Yeah, it's
from less than 50 to 50%.
so I'd call it like a sharp phase transition. It is pretty sharp. I mean, like even if you're at like so this is like 50%, and this is like, oh, I guess I drew it upside down. So this is like probability of failing. So this is kind of not very. Okay, probability of failing. Yeah, so even if you're at 49% or whatever, 49.9%, I think the probability of failing maybe even exponentially decreases with that. So yeah, so it is a pretty sharp. So for big N, it is a pretty sharp.
So it's like some exponential function of like the fraction, like
Yeah,
n times.
Yeah, as you get like
Yeah.
as you get like epsilon away from 50%, first off, the expected length of the hashing like grows I mean, I think it grows exponentially in 1 over epsilon. But then also get the probability.
It's interesting. I wouldn't.
You can say if you're keeping below load factor, like occasionally you'll hit this bad scenario of like, oh, we don't have an assignment, but then maybe you could rehash, like choose, like rebuild your table with new hash functions. That's probably what you do in practice. Any other questions?
Is there some clear reason for why the threshold is at 50%?
Okay, sure. So this will lead nicely into what I'll talk about later. Okay, so like imagine like I take my set of objects X and my set of slots Y. So like I could draw like the two hash functions.
Yeah.
Or whatever. And so for this, so you need this bipartite graph to have the perfect matching. And so it's like when it fails like Hall's condition, right? Like Hall's theorem. So it's like when the neighborhood has not enough neighbors there. Yeah, I don't know, it happens at 50%. I don't know, that's not too intuitive. They actually originally phrased it, we got two different hash tables, like you have one hash table of, like two different hash tables of size exactly n that the hash functions go to, and like one hash function goes to one hash table, one goes to the other. Okay, so there is the downside, right? Maybe I want my hash table to be more than 50% full for some, for some uses. I don't want to use twice as much space as the minimal. So that's why d-ary, this is what d-ary Cuckoo hashing does. So it was invented like very soon after cuckoo hashing because it's a pretty natural generalization. Instead of two hash functions, let's have d hash functions. Okay. Now, so then how does it work? So we insert our object to a random one of its hash functions. It kicks out the guy there. the guy who just got kicked out chooses one of his random hash functions and kicks out another. And so you just choose a random hash function at this point. There is other insertion algorithms you could do where you like pre-compute the shortest path of kicking out, but random is probably the best. You could like slightly optimize by saying, well, don't use the hash that you just got kicked out of, because then we might like just kick each other out a few times. But anyway, yeah, so that's the random. So this is random walk d-ary Cuckoo hashing. Hopefully, yeah, all the words in the title are now clear. So there is kind of a downside in that now we have to check D slots to see if somebody's there and to delete it instead of just 2. So you don't want to make D like too large. I mean, it should be like probably still a single digit number, really. But you can make it more than 2. And the advantage is, just like in the Cuckoo hashing, the magic number was 50%. You know, for every number of hashes, there is a magic number of for this, you know, for when we'll with high probability have a possible matching of objects to slots. So that was proven by like a bunch of independent authors, including my advisor, in 2009 to find the equations for them. So that's a couple of the values. And you see, even just going from 2 hash functions to 3 hash functions, now instead of 50%, our magic number jumps to 91.8%. So like, that's pretty useful. Now we can use over 90% of our hash table, and we still only have to check 3 slots to see if something is there. Questions on this algorithm?
Wait, so I don't quite understand. Sorry, there's a trade-off, right? Because if you increase to 3 hash functions, then also everything becomes like marginally slower, right?
Well,
By factor
search
3
and
halves.
deletion become slower by
Okay.
factor of 3 halves. Yeah.
So if you really care about the constants, then is there a trade-off there? Like,
There's some trade-off.
I guess I don't know exactly. Yeah. Okay, never mind.
Yeah, Richard?
Yeah, is there any study about like when you have 3, I just like when you have 3, what happens algorithm? Like I can say that no, I like, what about like the recourse? Like do you like, how much things do you change when?
Well, that's the subject of this talk, so great question.
This game is.
Yeah, so this is missing something that we had on the last slide, which is last time we said, and the insertion is O of 1 below the threshold CD. But I didn't say that on this side, that the insertion's O of 1. It's maybe not as clear because they're doing this whole like random walk thing. Yeah, what's the insertion time? Okay, so let's like remind ourselves the overall situation. So like we have this hash table that we like because it is quick search, insertion, and deletion, but we're not really sure whether it has quick insertion. You see I put this purple box, so we're not sure about that. Ideally, we want it to be O of 1. I mean, we don't even know if it's like O of log n, like a priori or whatever. So, but like ideally, we want it to be O of 1 for us to really say this is a hash table. But this method does have some other advantages, that our worst case search and deletion are also still O of 1. And our space is not just O of n, it's like n over some like explicit constant that can be made arbitrarily close to n by increasing the number of hashes. So yeah, so I don't know, seems like a pretty useful algorithm if we deal with the insertion. Okay, so there's been research on dealing with the insertion. So Fountelakis, Panagiotis, Steger. This was also based on our earlier work of Fries, Melsted, Mitzenmacher. They said anywhere below the ideal load threshold CD, the expected insertion time is polylogarithmic in n. And this paper, by the way, we build off like really heavily in my result that I'm going to present. So yeah, so I'm a big fan of this paper. I've read it a lot. Okay. But you know, ideally we don't want polylog n. Ideally we want O of 1. But definitely we have at least like polylog n, and they have like some like explicit exponent on the log that's like not too big. And so then the first to get like O of 1 is you know, again, my advisor with a former student. For any load factor. So if you say I want my hash table to be, you know, 99.9% full, eventually you can increase the number of hashes high enough, some number d that just depends on c. And such that the insertion time is then O of 1. So this is kind of maybe less useful in practice because, you know, if you want to say, oh, I want my hash table to be 99.9% full, this comes back to you with saying, okay, then use, 50 million hash functions, and then it works perfectly. But it was the first to get like an O of 1 insertion bound for some number of hashes. Walzer got, for at least for small number of hashes, which is what we want in practice, we get an O of 1 insertion bound up to, so this is what we want, O of 1 insertion. It works up to 81.8% full for 3 hashes. It's where the optimal value is 91.8%. So up to 91.8% full, there's an assignment, but it might take like polylogarithmic time to find it. Below 81.8% full, we can find it quickly, O of 1. So here's a table of these. So I tried to like kind of arrange the authors with what they proved. So like Pad and Rodler proved this first row for 2 hashes. And then this is, the first row is optimal. You can't do better than that. It's O of 1 up to the threshold. I mean, I guess you could try to make O of 1 better, but like, in terms of n, it's optimal. And then the load thresholds, I mean, this is just the answer. I mean, that's what it is. We've proven both sides. And the Walzer proved up to some load factor for each number of hashes, you get O of 1 insertion. Fries and Johansson proved this box, which is for large D, you have some load factor that gets you O of 1. And then Fountainlock, Panergiet, and Steger showed up to the ideal threshold is polylog for these like explicit exponents on log. That actually tend towards 1 as the D tends towards it. Questions on prior results? Okay, great. So this is the prior results. So I'm going to make it a little bit smaller so I can put something else on this slide, which is going to be the results after me and Alan's work. And what we proved is for 4 hashes or more, like 4 to infinity hashes, you get O of 1 insertion up to CD, which is like the threshold you wanted. We don't have it for 3, but at least we reduced the exponent on the log. Actually, that doesn't matter too much, really. I mean, polylogs. But like, but the main thing is for 4 hashes and more, we got O of 1 insertion up to the load threshold, the optimal threshold we could possibly get O of 1 insertion up to. Now, of course, the O of 1 could be better, but yeah. Okay. Questions on Alan and my result? It's on archive. You can go read it if you like. But of course, for the rest of the time, I'm going to tell you about. I'm going to tell you about my results, our result. Yeah. Okay. So no questions on what the result is. But first, we're going to take a quick commercial break, and I'll remind people or tell people for the first time that that there's a conference at CMU in 2 weeks about combinatorics. And so if you like combinatorics, you can come to this conference and see the talks. It's not as algorithmic, it's more just combinatorics, like it's just like math, but maybe you like it. And it's free, so you can show up. There's talks, and we have a website. So I'm one of the organizers, so is Olya, who's in the back. So yeah. Okay. Great. So let's talk about the proof. So I told you this representation before where like for you take your set of objects X and your set of hash slots Y, and you draw, every object in X gets, we can do it for like E equals 4 maybe, because that's what we proved. It gets like 4 random things, and this gets 4 random things. Every object is 4 random. Another way you could represent it is like as a random 4 uniform hypergraph or whatever, but I we'll stick with the bipartite representation. And so this is like, we could do combinatorics about this bipartite graph and say, hey, there's random, we're remembering we're taking our hash functions to be random. So every object just chooses 4 random slots. So what properties does this bipartite graph probably have? So let's talk about some of the properties it has. One we got from this 2013 paper is that for any delta that's O of 1, say it's like 1 over a million, there's some m such that all but n over a million vertices are within some constant distance of an empty slot. So if we go, where distance means like, like in the random walk procedure, not just distance of the bipartite graph, but actually in the random walk procedure with where things are. in M steps, starting from these vertices we can hit the end. So we know most things, 99% of things are not a problem because we can reach to the set of empty slots. Because our hash table is like whatever, 99% full, which means like, 1% of the slots are empty. So we can look at the empty slots, things that are distance 1 away from them, things that are distance 2 away from them. So the nice thing is this allows us to really only look at, so this is not like an obvious theorem. It's quite hard to prove actually, but I didn't have to prove it because it was already proven. Wonderful. So yeah, the barrier to Hull's condition at past the threshold turns out to be just that nobody has any edges going to the set of not currently occupied slots. But anyway, the point of this lemma is now we can focus on only the worst delta n vertices, because then if we stay on the good vertices, every time we take a step, we have like d-1 to the m chance that we'll just get to an empty slot in m more steps. So we don't have to worry about the part of the random walk that walks around on the good part. Okay, there actually is like a little technicality to this statement, but and really we can just focus on like the really bad section of the things far away, because the furthest thing away is going to be like log n many steps away. So there are some objects that are like quite bad in some sense. So we want to show we're unlikely to hit those. And so similarly, another set of slots, like if we want to say, oh, reaching some bad set is unlikely, it makes sense to say like there's no set that gets reached too much. So if I take any, so I could tell you, okay, before I give you what the statement is, like, how many times, so if I take like any one object, any one slot, how many times, like what's the maximal number of times any one object will be hit? So you're putting dn random hashes into like about n slots. So it's like n balls into n bins. So the worst object will get hit how many times? Somebody who knows n balls into n bins. Log n. Okay, close enough. Yeah. Let's just say log n. But what?
Is it accurate over log n?
For n ball, yeah, it's just log. It's just log. Yeah, okay. Okay, yeah. Yeah, so it's log. So one object will get hit, like one slot will get hit like by log many hashes. And so you can generalize this to like a set. If you take any set in here, it's going to be like a factor of like log of the size of that set of it. Then anyway, but so this is like a classic like Chernoff proof. Anybody who like, I don't know, does algorithms or combinatorics, you can probably figure this out. It's like Chernoff and union bound. So like for any particular z, you show it have like use Chernoff bound to say the probability that fails. So this isn't too hard of a limit.
What graph theoretically we're trying to prove? Or like what graph theory statement is equivalent to the Hashman result that you did?
So it's not, so I don't really think of it as a graph theory statement, but
Or rather it's like
yeah, if we take, it's essentially like a random walk. So we start off with some assignment of objects to slots. So like say this one is here and this one is here. And actually, given the random bipartite graph, we can take that assignment to be worst case. Which actually is it's not even clear. We could have done that, but we were able to prove it for the worst case starting assignment. Okay, so with this starting assignment, we started a random vertex, and then we take, or well, we started anywhere, whatever.
this random walk that does like switching.
Yeah, so your random walk, so when you're going this way, you choose a random one of your neighbors to go to. And then you land on some spot, and somebody is currently living there, and you kick them out, and then you choose a random, so it's like half random. So it's like you're random going this way, but not random going that way.
That is like, it's like 1% of the items are like super constantly far away from the empty set.
Yeah.
Aren't you in trouble if you start with those items?
Yeah. Oh, but we started a random slot. When we insert a new object, we started a random slot.
So if you have, with what probability do you want to like succeed in having an O1 walk?
O of 1 is the expected time of the walk.
I see.
Yeah,
It's not down the expectation.
Yeah, sometimes the walk will take log n.
I see. But like you particularly need to show that at most like a 1 over logarithmic fraction of the starting vertices lead to a log n.
Yeah.
Okay, thanks.
Yeah.
Okay, can I ask that? Sorry, this is a stupid question, but So you're saying you can actually fix, so when you say you fix a, like a worst case assignment, that's basically saying. It doesn't even matter if the assignment that you already, like the table you already have actually even came from some valid sequence of insertions and deletions and so on. It's just like something. But if you're fixing that assignment, then haven't you also fixed the randomness of the table, or is it like there are some entries that are?
First, we make the random bipartite graph. First, we
Okay.
throw all the random hashes.
Yeah,
And then, given that random bipartite graph, we assign each object to one of its hashes in a way. We find a matching in this graph.
given the red,
So first we create a random graph and then we, adversarial, we get a matching in that.
yeah, but then when you now say, given all this. Then something is expected O of one, what is the?
The expectation is over, when you like kick somebody out, the expectation is over, he chooses one of his other random hashes.
Random,
Yeah, randomly.
I see, so in,
It's not, so you can talk about like the BFS path to an empty vertex in there, but that was already proven.
I see, but so in the D equals 2 case, there's no expectation there, right? Then,
Yes,
sorry if I missed that.
yes, yeah, so the expectation only comes for more than. Except I guess you started a random one. For the D equals 2 case, so it can be expectation over what random.
Why do you start over there?
Well, we're adding a new object, like a new object comes in. And we're adding this guy, and so it just chooses some random.
I see. Okay,
Yeah, we can't, yeah,
Are you assuming right now that X is like 90, whatever that constant was, 91.8%, the threshold constant, the size of Y? Or whatever the constant is, I know it depends on
so
the,
X has
are
to
you
be,
assuming we're at that theoretical threshold?
well, we're assuming we're below that theoretical. We assume we're C full for some C that's less than CD.
Okay,
And so then this is at that C, as we take n objects and n over C slots. Then as n goes to infinity with that fixed C, it's O of 1. And D is also fixed. Okay. Yeah, so what are some other things we can prove about the bipartite graph? There's a nice like expansion property for every set here, set S here of objects. We know that the most number of neighbors it could have is D times S, if all of its hashes went to different things. So like, so if every guy in it has its hashes going in different places, we definitely have N of S is less than DS. Okay, but like theoretically, like all of, like in a terrible case, like all of their hashes could just go to one object. Like even for just one thing, if we're choosing its 4 hashes, we could choose, like 2 of them could happen to land on the same place. And in fact, this probably will happen, but what probably won't happen is that this will probably never happen. And so we prove some expansion property that for some X of S that's like less than 1, like very small. So we're basically the neighbors of S is about D minus 1 times size of S. And they proved that for some bound, and then we had to improve their bound just to get the, so theirs is just, yeah, so I don't know. So you just take union bound over S, union bound over possible Z that could be its neighbors and say, what's the probability that your neighbors are smaller than that? But we needed to improve this lemma in order to get the D equals 4 and D equals 5 case. When we first proved, we only got it for 6 and above. And then we improved some more and got the case 5. And then we improved some more and got the case 4. And we haven't gotten the case 3 yet. But maybe we can. Maybe we can. So that's still the open case.
So what do you get to, like, improve the concept?
Prove-
You get a type.
Prove O of 1 insertion for D equals whatever. We haven't proven it for D equals 3.
I see, so the actual value of the constant matters to prove.
This constant?
Yeah,
Yeah, it does.
like, I mean, if you have a constant, but it's worse, then you don't get the O of 1.
Yeah,
Okay,
it's kind of weird. It shouldn't be like obvious why that is, but it is. So if we were to reduce this A3 below 4, that's currently 8.1, And in my head, I know some way to get it to like 7.9, but if we could get it below 4, then we'd solve the d equals 3 case.
But you don't, do you definitely believe it's true for the experiment?
Yeah. I mean, it's got to be true that there's O of 1 insertion. I mean, it would be really weird if, yeah, there's got to be O of 1 insertion. I don't know whether our techniques to get it, or maybe you have to do it like some completely different way. I don't know. I also suspect that technique is similar. So, yeah, so anyway, yeah, so to improve this lemma, you need to like count surjections exactly using Stirling numbers. Like, what's the probability that the n of s is like exactly this set? You count the number of possible surjections to that set, and so it kind of gets a big calculation that, like, I don't know, takes like a page or two, but like isn't actually that hard. And then also you can say, like, what if like we also, instead of saying for any particular s, what's the probability it fails, you can say, what's the probability it fails and no subset if it failed, because we have to have some set like that if the lemma fits. So that's a hard lemma. Okay, but I haven't even told you like kind of like the main new idea of the proof. I should tell you that. Which is we define these bad sets, BI, and good sets, GI, that are like complex. So yeah, so we have this good set. So like, here's our objects or whatever. So we have this good set G that's like all but delta n, all but n over a million of our vertices, whatever. And so then GI, and so then we have like, you know, within this we get, you know, the B's are declining. So we have like B is a superset of B2, it's a superset of B3. Until eventually we get one of them's the empty set. But so the definition of these B is that they're good if at least, so if you take a walk of length I, you have like d minus 1 to the I possible places you'll end up. And so we're saying a 1 over I to the 0.99 fraction of those possible walks. So about a 1 over I fraction of those walks will end you up in the good set. So that's the good. So anyway, so that's our like, I don't know, biggest new idea, I think. I don't know. We have to prove that these BI have exponentially declining sizes. Yeah. Question on this definition? I guess things are getting more and more technical as we get to the end of the talk. I guess that's how it works. Yeah, questions? Yeah, so then when we prove that, so we prove that the size of the BI are exponentially declining using that expansion property. I said that the neighbors of any set like gets bigger by a factor of about d minus 1. And then once we've proven this main lemma, then we use that plus, you know, so we have our bad set BI, you know, sitting here, and to show it's unlikely to get to our bad set, we have to show like the bad case would be if like everything hashes to BI, that would be terrible. But you know, we have a bound on how many things can hash to one set. And so we can like iteratively apply that bound to say we're not that likely to reach BI in the first about I steps of the random walk. And on the other hand, if we don't reach BI, then every step we take has like, you know, every time we walk I steps, we have like probability about I ending up in G, and then we'd be good. So we're unlikely to hit BI, and if we stay out of it, we're unlikely to take more than I steps. So yeah, so BI kind of corresponds to taking I steps, the probability that will take more than I steps. Okay, I'll just go on. This is, oh yeah, and we also have some technicality about the BIs that, yeah, we had like we had to put a second version on archive because there's some technicality, like the matching changes over time, right? Things are assigned to slots, but then they get assigned to new slots as we're walking. And so basically that has like very little effect, but you have to write some lemma to show it has very little effect. Okay. Okay, future work. Let's get back to non-technical stuff. So we got to finish the d equals 3 case. We could make the O of 1 term smaller for sure. I mean, you know, we just tried to get rid of the n, but it definitely could have a better dependence on the number of hashes d or on the load factor c, or just a lower total constant, because I think there's some like constant of like a billion or something. And so this is what you're asking about, like tail bounds, so not just the expectation. We say the probability of the random walk taking more than S steps currently declines like e to the minus S to the 0.1. But ideally, it'd be nice for it to decline exponentially. It actually tends towards declining exponentially as d tends to infinity. But it'd be nice to show actually exponential decline. When we say with high probability, sometimes our hashes will fail this. And, currently our with high probability statement is like, it declines like n to the point, maybe 0.01 or something. But so that also kind of implies that you're robust to, if you stay at the load factor and delete some vertices and then add them, you could do like a union bound and say, probably we still have all of those properties. So that's some kind of robustness if you show that your with high probability statements are unlikely, are pretty likely. There's another generalization of cuckoo hashing that's pretty cool, where instead of just having more hashes, or like in addition to having more hashes, every slot now has like a constant, it has like a capacity that's like a small constant number, like say it has capacity 3 or something. We also know that like, you could add another parameter like C sub D, comma, whatever this letter is, as your load factor. So we know what the load factors are, but we haven't proven O1 insertion. So that's an interesting direction, I think. Unfortunately, like the Fountain-Lockett's kind of the Sager result like doesn't work in this scenario either. So I kind of like no longer have a roadmap to follow, but similar techniques should be able to prove some O1 there. Okay, that's the end. Thank you. Oh, yeah.
Do you think you could have like some sort of auxiliary structure that does a little offloading that allows you to not do a random walk, but like sort of identify possible walks that are more likely to?
Yeah, so it has been studied before, just so like one thing is just, and in fact, in the original d-ary Cuckoo hashing paper, they proved the bound for BFS walks, but which is where, once we get our new object with its random hashes, we just like compute the shortest hash getting there. And they proved that was O1, which is of course easier than proving random walks O1. I mean, we built off that though. But
you have to form the tree.
yeah, so the worst thing is that takes more like space overhead and time. And if you're actually like coding this up, it's probably nicer to just like choose randomly. Though I don't know, maybe it's not. Maybe there's some trade-off. Maybe you don't want to do all that many rehashes. Yeah, so there's other insertion algorithms. There's other things like, we don't want to fail this with high probability things, so we can have some like extra stash of like wherever we failed our matching, we can just throw those guys into some junk set and like, there's been other versions of d-ary Cuckoo hashing stuff. Other questions? Yeah.
So I guess there's a kind of a more general phenomenon. It's that like, so like the kind of problem that I looked at more is like there's big literature on dynamic matches.
No, and what is it? Oh yeah. So this is related to like like online bipartite matching.
Yeah, that type of stuff.
Yeah, so like online bipartite matching, like think about the recourse version, right? That has this like log squared n recourse. Yeah, so this is like especially BFS insertion, the insertion algorithm I was saying, where you find the shortest augmenting path like in the bipartite matching. Basically this is saying if you take a random graph instead of an adversarial graph that has a matching, this is like the average case version of online bipartite.
Well, so the one that I'm more concerned about is that people in general understand that like doing BFS, especially in dynamic like graphs, that has a lot of hardness kind of properties. Like, could you say some statement about like do you like I'm just wondering whether this translates to beyond like matches? Like, could you say something about like like a dynamic BFS or something? Like any kind of reasonable thing, like generative graph model.
Yeah, so yeah, I don't know. So I was wondering if you could like prove something about like random walk in like some, some worse, instead of just a random graph, if you choose some worst case graph and you do a random walk on that to assign a matching. There's relations between things, and this is probably not what you're saying, but just other uses. I mean, the relation between proving the threshold C sub D, it's also called like the orientability threshold of random hypergraphs. And so there's relations to that, to like load balancing, to XOR stack.